Okay, so in this lesson, we're going to be looking at the advanced rational functions, the ones that are a little bit more involved than the simple ones. So we're going to learn about the rational functions of this form right here, which is the same form as before. We have a polynomial divided by a polynomial. It just, in this case, the polynomial is in your general form, a sub n, x to the n, and so forth and so on. Okay, and then we have a different exponent down below. And so we're going to look at this and see what we can do here to help us graph these types. Okay, so what are the guidelines we're going to follow? So I'm going to list them all out here for you so you can write it all out so that you know exactly kind of step by step how you want to approach these questions. And this is exactly how we're going to do it with my examples. So what are our guidelines we're going to follow? Well, the first thing we want to look at is we need to factor the numerator and the denominator completely. This is important because it gives you some characteristics of the graph. Namely, it helps you find the vertical asymptotes and any points of discontinuity. So we're going to factor the numerator and the denominator completely down to linear factors. We're going to reduce any common factors. But if there is a common factor, then we have to write the reduced function. And then we're going to put a comma and then exclude the 0 from that common factor because that is also going to become a hole in the graph. If I cancel a common factor, it becomes a hole in the graph and not a vertical asymptote. Okay, the zeros of the common factors will become holes in the graph. At that value, the hole is called a point of discontinuity. So those are important to find if we have it. Once we have done this, then we're going to go into finding the vertical asymptotes. Again, before I can do vertical asymptotes, again, I need to make sure that the top, the numerator, and the denominator have no common factors. So don't forget to do step 1. And then we take the denominator, we set it equal to 0, and we solve for x. This is what we did last time where we took the denominator, set it equal to 0, and solve for it. And then we get our vertical asymptotes. And you can have more than one. Okay, once we do that, we're going to look at and find our horizontal asymptote, more importantly, our end behavior. So let's go ahead and change this name right here. It may be a horizontal, but it may not be. We're going to have an end behavior now because we may have something beyond a horizontal. So it's better known as an end behavior asymptote. But the first two are going to be horizontal. So what you do for this one is very simple. You look at the degree of the numerator and the degree of the denominator. If the top degree is smaller than the bottom, you will have a horizontal asymptote at y equals 0. That means if the top degree is a 4 and the bottom degree is a 9, I know I have a horizontal asymptote at 0. If the degrees are exactly the same, so if the top degree is a squared and the bottom degree is squared, then I'm going to have a horizontal asymptote at the value that's the ratio of the leading coefficients. So whatever these leading coefficients are, that ratio is going to be your horizontal asymptote. The last one here is what happens if the top degree is bigger than the bottom degree. If the top degree is bigger than the bottom degree, then you're going to have the end behavior asymptote is going to kick in and it's not going to be horizontal. In this scenario, there is no horizontal asymptote. The end behavior resembles a polynomial of degree n minus m. We are only going to look at what's called the slant asymptote. We're not going to graph anything beyond a slant asymptote, which basically means that the difference is going to be 1. So n minus m will equal 1, meaning we're going to have a diagonal line, basically, a slant. Okay? And we can figure out what that slant is going to be. We're going to use long division to help us do that. And I will show you how to do that also. So long division is used to help us find the slant asymptote. The degrees help us find the horizontal asymptotes. Once I do that, I want to find the x-intercepts. Take the numerator, set it equal to 0, and solve that. That will be your x-intercepts, or the x values of the x-intercepts. Find the y-intercepts. There is only one, or maybe not one. But to find the y-intercept, you just simply plug in 0 for x and solve. Once we do that, we're going to plot 1 point between and beyond each x-intercept and vertical asymptote. So in our table, in the simple one, we found the vertical asymptote. We did 2 numbers above and 2 numbers below. In this particular case, in our table, we're going to put every vertical asymptote and every x-intercept, and we're going to put numbers, find values in between those. So there may be more numbers in our table than we had previously, but we want to make sure that we have the right shape. You'll see some of these shapes can get kind of interesting. We're going to sketch the smooth curve. We're also going to use a calculator to assist us in this, so you can kind of see what the curve looks like ahead of time. And then that's what we're going to do. Okay, so we're going to practice this. We're going to go through some of the problems, and I'll show you how to go about doing this. So the first one we're going to do is we're going to look at this equation right here at the top. Okay, f of x equals a negative 12 over x plus 2 and plus 3. Notice this is in simple rational form. This is in simple rational form. Okay, and so we already know how to find most of this stuff already. We can see clearly that we take our x plus 2 set it equal to 0. We get x equals negative 2. So I know that negative 2 is my vertical asymptote. Okay. The plus 3 over here. So I know that my horizontal asymptote is y equals 3. And then we can graph this according to what we already know. And we have a vertical asymptote at negative 2. So we'll put that in the middle. This is my undefined. We pick 2 numbers above and 2 numbers below. This is what we did last time. And we plug these numbers in and we get some kind of fraction of some type. So if I plug in a negative 1 right here, I'm going to get a 1 on the bottom. So this gives me a negative 12 plus 3. A negative 12 plus 3 is a negative 9. If I plug in 0 here, I'm going to get negative 12 over 2, which is negative 6. And negative 6 plus 3 is negative 3. If I plug in negative 3 into this, I'm going to get a negative 1 on the bottom and a negative 12 on top. That gives me positive 12. Positive 12 plus 3, 15. And if I plug in negative 4 into here, I'm going to get a negative 2 here and a negative 12 on top, which gives me positive 6 plus 3, 9. And so then I can come over here with my table. I can put in the vertical asymptote at 2. Now, my scale here is a little interesting, but we're going to eyeball it as best we can. This here would be 2.5. I'm sorry. This will be a negative 2.5, so it's going to be slightly to the side of it. So we'll put it in vertical asymptote right about here. Okay, and then we have a horizontal asymptote at 3. So this is x equals negative 2. 3, this is 2.5, so this is B3 is be slightly above it. So there's my horizontal. This is y equals 3. And so there's my little 4 pieces, and I'm going to then use my table to help me figure out where these numbers are going to go. At negative 1, we're at negative 9. So this is negative 10 right here. This is, remember, was negative 2. Half that distance would be negative 1. So somewhere right about here is negative 9. And then at 0, we're at negative 3. We can do more points if you wanted to see where it is. What happens if I plug in a positive 1? If I plug in positive 1 right here, I'll get 3 on the bottom. Let me make a quick table here. If I plug in 1, I get 3 on the bottom. So that makes it negative 4 plus 3, or negative 1. So 1 is about here, and we're at negative 1. So you can see that but we can see where it's going to go. It's going to come from down here. It's going to curve around and go that way. And that's fine. Over here at negative 3, we have 15. So we're going to have a dot right about here. And then at negative 4, We're going to have a dot at 9, which is right about here. And we can keep on going, but we can see also that this graph is going to come down this way, curve around, and approach the end behavior over here. So there's that graph. Okay? Label a couple points on each branch. Here is 0, -3. Over here, we had -4, 9. Now, I showed you that one, so I can show you this one. Okay? This is in simple form. This one is in general form. Okay? But I want you to know that these are actually the exact same graphs. So let me show you why I know it is. You put something like this into this format, what you've literally done here, if you think about division, we get a quotient and then we get a remainder that we write as a fraction. So from long division that you learned in polynomials, this can be written as x plus 2 into 3x minus 6. So when we do long division, what times x gives me 3x? Well, a 3 gives me that. We multiply around, we draw the line, we change the signs, and then we add this up. This becomes 0, this becomes -12. This is the remainder, this is the divisor, and so my answer is written as the quotient plus the remainder as a fraction. And you can see clearly that this and this are exactly the same as that. So all of these are exactly the same problem. So if I graphed this one, I would have the same answer over here. Okay, so I just wanted you to be aware of that you can change different forms. I don't recommend it. Just leave it in this format right here, and we answer all the same questions that we did before. Okay, so let's walk through the process that I showed you before on how to go through those. That's what we did before. Here's what we're going to do now. Let's graph this one. So according to our steps, the first thing I have to do is I need to factor the top and the bottom completely. The top is already factored. Factoring just means to write as a product. This is all a product. There is no pluses and minuses. And this down here is the difference of two squares. So that'd be x plus 2, x minus 2. And I look at this and I see, okay, there is no common factor. Since there is no common factor, we're good to continue. We're now at step 2 where we're trying to find the vertical asymptotes. The vertical asymptotes occur when you set the denominator, x plus 2, x minus 2 equal to 0. So when I set it equal to 0, I solve this. So this is a factored form. That means x plus 2 equals 0, or x minus 2 equals 0, x equals -2, or x equals +2. And these are your vertical asymptotes. Those two. So we have 2 of them. Okay? Once we do the vertical asymptotes, then we do the end behavior asymptote or horizontal asymptote. We look here and we notice, hey, these are the same degree. Since they are the same degree, then the horizontal asymptote is going to be the ratio of the leading coefficients. So we go look over here. What is our leading coefficients? I know I'm going to have a horizontal asymptote. So it's going to be y equals, it is a 2 divided by a 1. 2 divided by 1 is 2. So we have a horizontal asymptote at 2. So once we've done that, then we want to find the x-intercepts. The x-intercepts occur when the top, the numerator, is equal to 0. So we take the top, 2x squared, set it equal to 0. And when does this have to equal to 0? It only equals 0 when x equals 0. Okay? So remember, this is an x-intercept. The y value of x-intercepts are always 0. You just found out that the x value is at 0. Intercepts are points. Do not list them as equations. List them as a point. Your x-intercept is at 0, 0. So we can also check the y-intercept to see if there's but we already know what it's going to be. We know it's going to be that. There's only one y-intercept, and if this is where it's at, we know it's here. But the process is simply to plug in 0. If I plug in 0 into this equation, I get 2 times 0 squared, and then I get 0 squared minus 4. The top is 0, the bottom is negative 4, and this is 0. Confirming that indeed that the y-intercept is at the point 0, 0. Once again. Okay, so what's next is we want to make a table. Okay, let's make our table here. In our table, we want to have in our vertical asymptotes, our x-intercept, okay, and some points in between. So if negative 2 is the smallest number, then I need a number to the left of that. So this will be negative 2. Then I need a number. Then I need to have 0, which I already know is at 0. Okay, then I skip a space, and then I put in the next vertical asymptote. So these are all undefines. And then I need to have a number to the other side of it. So we need to plug in numbers in between these. So what's between 0 and 2? Well, 1. What's beyond 2? 3. Negative 1. Negative 3. And so these numbers are the ones I need to plug into our table. Now, you can do this by hand and get this answer this fine. And Danny, you can also use the calculator to assist you. Remember, these graphs are going to have different branches. Okay? I have no problem if you use the calculator to type in this original function. And then this gives you an idea what it looks like. You can also use your Desmos to assist you with this. So I see right here, see, I'm going to have 3 branches. This is what it's going to look like. Okay? So what I need to do is I need to find values in between here. So to do values, I simply do the trace feature on my calculator. Okay? See, there's the 0, 0. I want to find negative 3, so I just type in negative 3 and hit enter. And it gives me 3.6. So negative 3 is 3.6. And then I'm going to type in negative 1. And I get a negative 0.7. At 1, I get a negative 0.7. And at 3, I get a 3.6. And if you want to do more numbers on there, you can, just to make sure. What happens if I type in 4? I get 2.7. Okay, 2.7 if I do 4. And this gives me an idea what the shape is. I see what it looks like. I see what I have to draw. I have some points to help me put it in the right spot. That's why we do it that way. Once I have my table, I'm ready to do my drawings. The first thing I plug in, I type my drawn here is all the asymptotes, whatever they are. So I have a vertical asymptote at 2. I have another one at negative 2. So here is x equals 2. Here is x equals negative 2. I have a horizontal asymptote at 2. So we draw that one. And we label that y equals 2. We have a dot at 0, 0 as my x and y intercepts. And we can plug in the rest of these dots. So I already knew the shape of this thing. I have a branch over here, a branch over here, and a branch that does this. And so at 1, we have a negative 0.7 about here, at negative 1 right here, which confirms that it does indeed go downward in that fashion. So draw the curve down, get close to the vertical asymptotes. There's a branch that's done. Over here, we have a dot at 3.6 from 3 to 3.6, which is about right here. Okay, and we can actually do 4 is at 2.7 if you want it. And that shows me that this branch is going to do something like this. So here is 3, 3.6. This was 0, 0. And then when over here we had at negative 3, we had a 3.6 also. And likewise over here at -4, we would have it 2.7 because it was symmetric. And we can draw this curve. So it has to come down this way, curve through those points, and get closer over there. And so here is a -3, 3.6, and that graph is complete. So the only thing left to do at this point is to determine the domain and range of these functions. Because these are a little bit more complex than the simple one. The simple one we just simply threw out, like here, the domain is all the real numbers, x does not equal this one vertical asymptote, and the range is all the real numbers excluding the horizontal asymptote. But look at this one, it's a little bit more challenging. The domain is fairly simple. It's all the real numbers. X does not equal plus or minus 2 for the vertical asymptotes. Those are usually pretty straightforward. But the range is a little bit more complex because there's a gap here. It's not a single at 2. There is no y value in this whole entire gap. Okay? There's nothing here. So we need to be able to write this so that we can see exactly where the graph occurs on the y-axis. Well, the y-axis, the graph occurs from 0 downward. So it's all the real numbers. Y is less than or equal to 0. That's this piece. And y is what? Above this horizontal asymptote. So it's above that. Okay? So the y values are going to be greater than, but not equal to, 2. So that is the domain and range for these. Below 0, including 0, because that's the dot, and above 2, but not including the 2, because that's a horizontal asymptote. And that's domain and range. And we'll talk more about those when we do some other ones. I have another example right here. And so let's start this one from start to finish. All of these have interesting little things that will help you get through the rest of the problems. So what is the first thing I have to do in any one of these problems is I need to factor completely. So that means I need to factor the top, I need to factor the bottom. The top is a quadratic that can be factored. The bottom is already factored. The top is x, and I need two numbers that multiply and give me 4, and subtract and give me a 3. So one will be a 4, and one will be a 1. So this will be plus, and this will be minus, and there it is factored. You'll notice there are no common factors. It's good. Okay, so here we go. What is the first thing that we do after we check to see if there's common factors? We got to do the vertical asymptotes. So for the vertical asymptotes, I take the denominator, x minus 2, set it equal to 0, and solve. And that gives me the equation x equals 2, which is my vertical asymptote. The next one is I look for is the end behavior or horizontal asymptote. So I look over here at the degree. The top degree is 2, the bottom degree is 1. So the top degree is bigger than the bottom degree. When the top degree is bigger than the bottom degree, there is no horizontal asymptote. It's going to be an end behavior, and for our purposes only, it will be a slant asymptote. And to find the slant asymptote, I need to do long division. I got to find the quotient in a long division problem, not the remainder, just the quotient. Which means I will come over here for the end behavior, which we already know it's a slant, so I'll just call it a slant. We're going to do long division. So x minus 2 is the divisor. X squared plus 3x minus 4 is the dividend. Okay. What times x gives me x squared is an x. Draw the line, change the signs, add this up. This is now 5x. Bring down the 4. Repeat. Plus 5. 5x minus 10. This gives me a remainder of 6, but I don't care about the remainder. I only care about that right there. My slant asymptote is going to be y equals x plus 5. So we have a slant at x plus 5. After that, we want to look for the x-intercepts. Could be more than one. X-intercepts are when the numerator is equal to 0. So we take the top. Since we've already factored it, we'll just set it like so. And we set it equal to 0. And we get to see that the two zeros that come out of this are at x equals -4 and x equals 1, which means I have an x-intercept at -4, 0, and at 1, 0. We have two x-intercepts. We want to look for the y-intercept. The y-intercept is when I plug in 0 for x. So what is k at 0? It will be 0 squared plus 3 times 0 minus 4. On the bottom, I'll have 0 minus 2. So it's going to be -4 divided by -2, which is going to be +2. 0, 2 is my y-intercept. Okay? And so the next thing I need to do is I need to go through here and make my table so I know how I'm going to graph this out. I have a vertical asymptote at 2. So there's only one. We'll put it here in the middle. This is my undefined. I should give myself some more room. Give me a minute. I forgot about the x-intercepts. So we have an x-intercept at -4. And then we have another one at 1. Then we have a y-intercept at 0. Okay. And then we have another one at 1. And then we have 2. And then we need to have a number out here. So we want to plug in -5, negative something. Let's do -1. Let's see what happens here. Is going to be a fraction, 1/2. Here will be another fraction, 1.5. Here will be a number. Let's try 3, and we'll see where we go from here. Now, you can also use the graph that you do on your calculator to assist you in making your table. Also, that's fine. So I've already graphed this so you can see what it looks like. If I type it in the calculator, I'm going to see this. So you need to be understanding here that all of these graphs are going to have more than one branch, okay? Unless something interesting, as long as there is a vertical asymptote, okay, you're going to have branches, all right? Since we have one more than you actually have. So we have one vertical asymptote, so we're going to have two pieces, two branches. But when I graph, I only see one of them. That means the other one is you're not seeing it. You need to zoom out so that you can see where it's at, so that it can assist you in your graphing. So we can go into our window settings, number 4, and we can change our windows. You can zoom out until you find it, whatever the case may be. I've already done this one, so I'm going to just go right into it and set my window. I'm going to do x at -10. Actually, we'll just do it at -15. And then we're going to go up here to +15. Down here, we're going to go to -15. Up here, we're going to go to +20. And we can see that the other branches over there. Okay? If you notice, there's the vertical asymptote right there. And you can see the slant asymptote right there. Okay? And so we're going to put all this stuff in there. We can do a trace feature to find some of these numbers. So if I type in the trace, okay, 0 is 2. We already know this. So I'm just doing the trace feature here. We plug in these numbers over here. We have a vertical asymptote here. This is undefined. We have -4 is 0. 1 is 0. So we type in 3, and I get 14. 1.5 is a -5.5. 1/2, 1.5. -1 is 2. -5 is a -0.9. Okay, we can put more numbers in here if we want to, but let's put in our vertical asymptotes and all of our asymptotes and see how this works. Okay, so we have vertical asymptote at 2. So again, it's by 5s here, so 2 is going to be right about here. So this is x equals 2. I have a dot at -4, 0, which is right about there. I have a dot at 1, 0, which is right about there. I have a dot at 0, 2, which is right about there. Okay, and then I have a slant. So the slant is a dotted line also. It's x plus 5. That means I have a y-intercept at 5 and then a slope of 1. Okay, so remember as you do this that this is going by 2.5, so up 2.5, over 2.5. So this is the dot, up 2.5, over 2.5. So we're following this diagonal right there. So make sure you put it in there and you draw it as neatly as possible. And then you draw that down. That is your slant or in behavior asymptote. And that is y equals x plus 5. So we saw what the picture looked like right there. All right. So there's a couple things we want to look at to make sure we know exactly where things are going to go. This will also help us in figuring out the range. Because you'll notice in this picture right here that there's a gap between these two. So what I need to know is I need to know what is the maximum value here and what is the minimum value there. So I have to do that on the calculator to determine these values. So you go to menu, analyze the graph, and we can do max and mins right there. So I'm going to do the maximum one first. I'm going to slide this one over to the left of where it's at. Hit enter. Then I'm going to slide it across, and the dot's going to form. And when the dot stops moving, I can stop. And so there is, and you can grab these, by the way, on these calculators. Slide it out of the way. So that is that point. That's the maximum point. I don't know some reason why it's highlighted. Then we're going to go over here and we're going to find another one. This one's the minimum. I need to be to the left of where I think the minimum is. And then I slide across. It will give me a dot. It'll stop moving. That's where it actually occurs. And we'll need these for later. Okay, so keep those in mind. We'll come back and reference those later and help us with our domain and range and stuff like that. But they also give us 2 more points on here. So I know at basically 4.4, I have a dot at 11.9. So somewhere right about here is that minimum. At 3, I go to 14, which is somewhere right about here. And so you can see how it's coming down. So it's going to come down this way, curve, and then go off in this direction. Down here we had a dot at a -0.4 and then 2. So somewhere right about here. So this dot here is pretty close to where it is. And so it's going to hug this line, come up to this point, curve around, and go down this way. So there's the 2 branches. You can label any one of these points. It doesn't matter. Here's 0, 2. This over here we had 3, 14. Okay. But these points right here are going to help us with our domain and range. Our domain is pretty straightforward. It's all the real numbers. That was weird. So it's all the real numbers. X does not equal 2. But our range is a little bit more complex. It is all the real numbers. The y values lower than that, and the y values greater than that. So it's going to be all the y's that are less than or equal to 2.101, and the y's greater than or equal to 11.899. So that is how you can find the domain and range using your calculator. Okay? And then I have one more example I want to look at. But I'm not going to be I'm not going to spend the time here. We'll continue this one during class time. But I want to point out that there is a problem in our classwork number 1, which is this one right here. And this one is going to actually have a hole in the graph. And I want to show you how that first step looks. So here's f of x. We'll have x squared plus x. And then this will be x squared minus x minus 2. So our first step is to factor everything completely. The top has 2 terms, has a common factor of x. And this gives me x plus 1. So there's the top factor. The bottom can factor into x and 2 and 1. I need that to be minus and that to be plus. And so what you notice here is that I have a common factor. Okay? When this occurs, you want to reduce this factor out. And this becomes then, this is how you write it, x over x minus 2, comma, and the 0 from this, what value of x makes that 0 is negative 1. You need to write x cannot equal negative 1 because it's in the bottom, so it can't be 0 in the bottom. But if I remove it, you can't see it anymore, so you don't know that it was there. So you need to tell me that it was there by telling me that x cannot equal negative 1. This will also continue off into your domain, so don't forget it. You have to show that this way. This is how you need to write it. So the graph, this graph, and this graph will look identical, except at one point, at negative 1. This graph will have a hole in the graph. And when we do this together in class, I'll show you how you can do all that and graph that out. You simply just going to put a hole in the graph, like if I was going to draw it. And let's say this was negative 1 right here. I would put a hole in the graph and then continue on. So it would look like that with a hole in the graph. We would then figure out, for the range purposes, remember there's no graph here at that point, so we got to figure out the y value that goes in there. And the way you can do that, so please write this down. The way you do that is just take negative 1 and plug it into here. So this point, this hole, is going to be at negative 1, and then you plug in negative 1 to here, you're going to get negative 1 over negative 3, and it will be 1/3. So that is the value of the hole, and you'll need that information to help you with your domain and range. Okay? So that's how you deal with that. So be aware, and we'll continue more of this together in class.